Hello RubyKaigi. I'm Peter, and I'm a Ruby core committer and production engineer at Shopify on the Ruby infrastructure team.
And I'm Matt. I'm also at Shopify, and I'm a senior engineer also in the Ruby infrastructure team.
For the last few months, we've been working together to make some improvements to how memory is laid out in Ruby.
In this talk, we're going to summarize the work that we've done so far, the challenges that we've faced, and where we're heading in the future.
But before we can go into detail, we're going to provide some background on how Ruby's garbage collector structures and manages memory.
The primary unit of storage in the Ruby heap is an RVALUE. An RVALUE is a C struct that holds one Ruby object. It's always 40 bytes wide, and it contains a union of all the possible Ruby core types, each of which has their own data structure within the union. So we could have a struct representing a string, or an array, or a class, and so on. The RVALUE itself is really just a container for our objects. Let's look more closely at one of the object types. The first 16 bytes of every type are always the same, an 8-byte field called flags, followed by an 8-byte class pointer. The remaining 24 bytes are different for every type. Our class objects store a pointer to an extension object here. Strings can store the actual string content, and so on. These RVALUEs are organized into regions called pages. A heap page is a container for a 16 kilobyte memory region. The number of slots per page can be either 408 or 409, and I'm going to hand wave over why at this point. But the important thing about a heap page's memory region is that all the slots are contiguous. Their memory addresses are 40 bytes apart, and that there are no gaps between the slots. Initially, when the heap page is created, all the slots will be filled with RVALUEs containing a special internal type called tNone. This type represents an empty slot. It contains only flags and a pointer value called next that can point to another RVALUE. This allows these empty slots to be linked together to form a data structure called the freelist. When a heap page is initialized, Ruby walks up each page, visiting each slot in turn. As it gets to each slot, it sets a pointer on the heap page called the freelist pointer to the address of the slot, and sets the slot's next pointer to the address of the previous slot it visited, creating a linked list of empty slots. When we need to allocate an object and we need an empty slot, Ruby asks the heap page for the first slot on the freelist. The heap page returns the slot, and then the freelist pointer is updated to point to the next slot in the list. This unlinks our slot from the freelist and allows us to put data in it. The use of a freelist keeps this part of object allocation a constant time operation even when a page is sparsely populated. Because if the page has at least one empty slot, the freelist is guaranteed to point to it. But, eventually, our heap pages are going to run out of slots, and this is where the garbage collector takes over. If the free list is empty when Ruby tries to allocate into the page, it must mean there are no free slots left on that page. So Peter's going to tell us about how the garbage collector runs in that case to reclaim space from the objects on that page that are no longer in use.
Now that we've looked at how memory is laid out inside Ruby, let's look at how Ruby's garbage collector works. Ruby's garbage collection phase consists of three distinct phases: marking, sweeping, and compaction. The last phase, compaction, is optional and does not run unless manually enabled. Ruby's garbage collection is stop the world, meaning that Ruby code is not executed when the garbage collector is active. The garbage collector in Ruby is fairly complex, so we can't possibly cover all the technical details in just a few minutes, but we'll provide a very high-level overview that contains all the information you will need to know for this talk. Let's first look at marking. Marking is the phase where we determine which Ruby objects are alive and which ones can be freed. We first mark the roots, which include things like global variables, classes, modules, and constants. We then recursively mark unmarked children of the marked objects until the mark stack is empty. Let's see an example of this. Here's a toy example of a heap with 2 pages with 7 slots on each page, with a total of 10 objects labeled A through J. Slots with no label means that the slot is empty. The arrows indicate references. For example, the arrow from object J to object D means that object J holds a reference to object D. Examples of references could be the contents of arrays or instance variables of objects. The first step of marking requires us to mark the root objects. The root objects here are objects A and B. Let's now mark these 2 objects. Since both objects are unmarked, we mark it black and place it on the mark stack. Now that we have marked all the root objects and our mark stack is not empty, we can start popping objects from the mark stack and marking its children. Here we pop object A from the mark stack and mark its children, which is just object C. We then mark object C black and place it on the mark stack. We now pop object B from the mark stack. It only has one child, which is object G. We mark it black and push it on the mark stack. Now let's pop object C from the mark stack. It has one child, which is object G, but since object G is already marked, we do nothing. We only have object G on the mark stack. Let's pop it. Object G has two children, objects F and H. Since both of these are unmarked, we mark both of them and place them on the mark stack. Let's pop object F from the mark stack. It has no children, so there's nothing to do. Let's pop object H from the mark stack. It has one child, object G, which is already marked, so we do nothing. Now that the mark stack is empty, it means that marking is complete. Now that we finished marking, all marked objects are live objects and all unmarked objects are dead and can be reclaimed by the garbage collector. We can simply scan the slots on the pages and free the ones that are not marked. Let's continue to use the example we used for marking. Here we move our cursor to the first object in the page that is not marked, object D in this case. We can free the object and reclaim the memory. We then continue to move the cursor until we reach the next unmarked object, which is object E. We've reached the end of page 1, so let's move to sweep page 2. Again, we move the cursor until the first unmarked object is reached, and we'll free object I. We can continue to move the cursor until we reach the next unmarked object, which is object J. Now that we've swept all the pages, sweeping is complete. Manual compaction was a new feature introduced in Ruby 2.7 and further improved with automatic compaction in Ruby 3.0. However, this feature remains optional and is turned off by default. Compaction moves objects within the heap to the start of the heap. This has several benefits, including reduced memory usage, faster garbage collection, and better copy on write performance. Ruby uses the two-finger algorithm for compaction, which I will explain in more detail. The compaction algorithm involves two steps, the compact step and the reference updating step. The compact step uses two cursors, or fingers, which is where the name two-finger comes from. The two cursors are called compact and free. The free cursor starts at the beginning of the heap and moves forwards, while the compact cursor starts at the end and moves backwards. When these two cursors meet, this step is complete. The next step is the reference updating step. In this step, we scan all the objects and update the pointers that have moved. Let's see an example of compaction in action. Here, the white arrow is the free cursor and the black arrow is the compact cursor. The free cursor starts at the beginning of the heap, and the compact cursor starts at the end of the heap. The free cursor moves forward until it reaches the first free slot, and the compact cursor moves backwards until it reaches the first live object. It will then move the object at the compact cursor to the free slot and leave a forwarding address at the original object to remember where this object was moved to. We'll use this when in the reference updating step. Let's move the free cursor forward and the compact cursor backwards. We move object G to slot 4 and leave a forwarding address. Let's move the free and compact cursors again. We now move object F to slot 5 and leave a forwarding address. Let's move the free and compact cursors again. The two cursors have now met, meaning that the compaction step is now complete. But we're not done yet. We must do the reference updating step. Let's say our object references look like this, where the arrows indicate that a particular object refers to another object. We now have just one cursor that scans the objects linearly. We check the references of each object that we scan and update the reference if it points to a forwarding address. Here, object B has one reference to forwarding addresses. By reading the forwarding address, we can update this reference to the correct one, which is object H. We scan forwards again, and we see that object C holds two references to moved objects. We can update the references of object C to point to the correct ones. We keep on moving forward and scanning. When we reach the end of the compacted region, we start encountering free slots and forwarding addresses. We can now safely reclaim these forwarding addresses since we don't need them anymore. We'll reclaim slots 7, 8, and 11. So that's how the garbage collector works. But throughout this talk, we've been referring to slots as always being fixed size, and Matt's now going to talk about how we handle the case where the object needs to store additional data.
So as we heard, Ruby objects aren't always a fixed size, and they don't always fit in a slot. There are two scenarios to consider: when the objects fit inside the 24 bytes at the end of an R value, and when they don't. We'll look at two strings, hello world, which is 12 bytes, and hello RubyKaigi, thanks for having us, which is 37 bytes. When we allocate the string, Ruby checks the requested string length against an internal constant called rstring_embed_len_max. And if the requested length is shorter than rstring_embed_len_max, which it is in this case, it just pushes the string data straight into the remainder of the slot after the flags. When the string is longer than rstring_embed_len_max, Ruby sets the noEmbed bit on the flags. This signifies that the data inside the R value is not the actual string, but a pointer to a separately allocated memory region containing the requested data. It then uses the system malloc call to reserve a new memory region outside of the existing Ruby heap. It stores the address to that memory inside the R value, and it copies the string data to the newly malloced memory. And with that, we've looked at the main way Ruby stores objects in memory. We've also seen how the garbage collector helps us keep our memory in order by recovering space from objects that are no longer being used. Now, Peter's going to talk about some of the challenges with a memory layout like this, and introduce our project, Variable Width Allocation, which attempts to address them.
Let's discuss some bottlenecks that exist within the Ruby heap that we aim to tackle with this project. The first issue is that a Ruby object often requires multiple pieces of memory to store data. You've just seen an example of this with the string example, where the contents of the string exist in a separate location than the string object itself. This results in poor cache locality. Additionally, this memory is often acquired through the system using malloc, which has a performance impact. We often think that the CPU only has a single level of memory, but that's not true. In order to improve performance, there's faster memory built onto the CPU itself called caches. These caches are further divided into multiple levels, usually 3 levels. The lower level the cache, the closer the cache is to the CPU core. By being closer, the electric signal travels a shorter distance, so it has better performance. Let's see how CPU caches work on a hardware level. Here we see a shot of the CPU die. We can see that the CPU has 8 cores, 4 on each side. Let's zoom in on one of these cores. We see at the bottom right corner there is a level 1 cache. By physically being on the core itself, the distance is very short. However, this limits the capacity of the cache, so the cache is very small at 32 kilobytes. Next, we see the level 2 cache to the left, beside the CPU core. This is further from the core than the level 1 cache, but it has more space, so it has a larger capacity at 512 kilobytes. Let's zoom out again. Here we see a very large region of level 3 cache that is shared between all the cores. The level 3 cache has a much larger capacity of 32 megabytes. Let's talk a little bit about how CPU caches work. Whenever a piece of memory is fetched from the main memory, it is also stored in the CPU caches. It's important to note that data is fetched from main memory in units of cache lines, which on the x86 architecture found in Intel and AMD CPUs is 64 bytes. What this means is even if you need just a single byte of data, all 64 bytes is fetched for you. When the CPU cache is full, it will overwrite the least recently used data to make space for the most recently accessed data. Two terms that is used is cache hit for when a piece of data that we access exists in the CPU cache, so we don't need to access the main memory, and conversely, a cache miss is when the data does not exist in any caches, so we need to do a very slow read from the main memory. As you might expect, a very important metric for optimizing performance is to increase the cache hit rate, so we need to read from the slow main memory less frequently. Let's see the cache performance of the current Ruby implementation. Let's use the example of an array. In the current implementation, the array points to a region of memory in the system heap acquired through malloc to store the contents. Our array has 4 elements, so we need 4 pointers to Ruby objects. Since each pointer is 8 bytes on a 64-bit system, we need 32 bytes of memory. The object occupies one R value, which is 40 bytes, and the content occupies 32 bytes. In order to read the elements of this array, we must do 2 memory fetches to fetch 2 cache lines. Acquiring memory from the system heap using malloc is not free. It comes with performance overhead, so we want to minimize the number of times we call malloc. Malloc also requires space for headers that store metadata when allocating memory, which may add up and result in increased memory usage. We're not the first ones working on trying to tackle this particular issue. Ruby 2.6 introduced a second heap into Ruby called the transient heap that aims to speed up Ruby by reducing the number of malloc calls. It was successful at improving performance, and some benchmarks saw performance improvement by up to 50%. However, the transient heap has technical limitations and cannot be a true malloc replacement. One of the major goals of this project is to improve the overall performance of Ruby by letting Ruby control its memory layout rather than calling the malloc system library and relying on the system to manage memory. Since Ruby's garbage collector is aware of the memory structure of each type of object, it can optimize for faster allocation and better efficiency. By placing the contents of the object right after the object itself, we can improve cache locality. By allocating dynamic size memory inside the Ruby garbage collector, we can avoid malloc system calls and thus be able to improve performance. Now let's look at how the memory layout changes when we use variable width allocation. Here we see the array example again. What this project aims to do is to move the array's data from the system heap to the Ruby heap right after the object itself. So what does this accomplish for us? Well, we remove the need to do a malloc system call when creating the array object. Let's see if we improved cache performance. Again, recall that every Ruby object requires allocating a RVALUE, which is 40 bytes in size. Our array data itself is 32 bytes. By placing the contents of the array right after the array itself, we can now access the first 3 elements of the array while remaining in the same cache line.
So far, we've merged 2 fairly large PRs into Ruby. Our first contained the infrastructure required to move data that would previously have been allocated on the system heap into a heap page alongside its RVALUE, as well as a reference implementation in RClass. The second improves this by changing the way the heap is organized to better facilitate variable width objects. The first thing I should point out is that this is only suitable for testing right now. Definitely don't use it in production. But if you want to play with this, you can enable it by compiling Ruby with use rvargc in your C flags. Let's walk through some details of the changes we've made. We're going to talk about class allocation. These 2 scenarios both allocate RVALUEs containing class objects. A class has data attached to it: instance methods, class methods, instance variables, and so on. Ruby creates a separate data structure to store references to these, called RBClassXT. It's a fixed size of 104 bytes and is allocated by malloc on the system heap. The code before our patch looks like this. Here's where the RVALUE is allocated, and this zalloc call uses malloc to allocate the extension object. This is what the code looks like after our patch. You can see that we're calling a different new object of entry point, and this one takes a payload size. This is the size in bytes of the object that we wish to allocate next to our RVALUE. So 104 bytes for the class extension in this case. When we call this new function, Ruby's allocator allocates enough memory to fit the requested size and the original RVALUE. But how does the allocator work? Remember that Ruby's heap is divided into pages, and each page is made up of slots. We've changed the garbage collector to introduce heap pages with slot size other than 40 bytes. And to do this, we built a new structure called a size pool. This is a collection of pages with a particular slot size. This slot size can be a power of 2 multiple of the RVALUE size, so 40, 80, 160, 320, and so on. We chose powers of 2 because they are the easiest to work with and efficient, since we can use bit shifting instead of more expensive mathematical operators to calculate them. And we multiply our powers by the RVALUE size so that we don't waste space when allocating just a single RVALUE. Objects that don't require variable width allocation will only need a single RVALUE's worth of space, so 40 bytes. Had we just used powers of 2, the smallest usable size class would have been 64 bytes, which wastes 24 bytes per object. Here's a diagram with the 4 size pools. Their page slot sizes are labelled. Now, say we want to allocate a class object. We first need to calculate the size pool in which we're allocating. A class object will need 144 bytes of space, 40 bytes for the RVALUE, and 104 bytes for the RBClassXT struct. This is 3.6 RVALUEs, which we round up to the nearest power of 2, so 4 RVALUEs worth of memory, which puts it in the third size pool. If we zoom into this pool, each size pool has its own collection of pages and holds a free list. Once we've chosen a pool, allocation can then work like normal. We allocate into the head of the free list and push the free list pointer onto the next element. But now we have a slot that's large enough that we can allocate both our class RVALUE and the RClass XT struct into the same slot. And that's how an object of dynamic size can be allocated using variable width allocation and our pool size strategy. In this case, we do waste about 16 bytes at the end of the slot, because we only used 144 bytes, and the slot size in the pool we allocated into is 160 bytes wide. But Peter's going to tell you about some benchmarking that we've done of runtime and memory performance, and what impact all of this actually has.
Our benchmarking was done on a bare metal Ubuntu machine on AWS. Railsbench and rdoc generation was benchmarked using the glibc and malloc allocators. glibc and malloc are implementations of the C library function called malloc, used to allocate memory. Different allocators are implemented differently, and so they have different properties. glibc is the default allocator in Ubuntu. If you're interested in looking at more in-depth results and analysis, check out the ticket linked in the slides. In Railsbench, we see a slight increase in memory usage when using glibc and malloc. However, we also see a small performance increase when using malloc. This graph graphs the RSS, or resident set size, which is the amount of memory held in RAM. The branch and master have their RSS graphed over time for 50 runs of Railsbench. rdoc generation generates the Ruby documentation. Unlike Railsbench, where variable width allocation used more memory, here we see 13% lower memory usage. In the liquid and opt-caret benchmarks, we see no significant performance differences beyond the margin of error. Now that you've seen our current implementation and performance results, Matt will now talk about some limitations of this implementation and how we're planning on tackling them.
The first area to address is the coverage of variable width allocation. Currently, only classes are taking advantage of this feature. In order to see the best performance benefit to Ruby application performance, we need to have more types using VWA. Before we can add support for a lot of other types, however, we need to tackle a limitation of the current implementation. We're currently unable to handle objects that need resized, and this makes mutable objects like arrays and strings problematic. Resizing is a difficult problem to tackle, and solving this problem will be one of our next major milestones. We do have a few ideas on how to implement resizing support. One idea is to allocate the new data 40 bytes into a slot in a page in an appropriate size pool, and then rely on GC compaction to move the RVALUE next to its data again. In addition to this, another milestone we would eventually like to hit is to shrink the RVALUE struct itself from 40 bytes to 32 bytes. Doing this would mean that our values are always aligned with CPU cache lines. For example, in the diagram, we can see that many of the 40-byte slots will straddle 2 cache lines. And now, if the slot size was shrunk to 32 bytes, all the slots are aligned on a single cache line, so reading a slot will never require more than one cache read. However, there's still a lot of work we need to do to get to this point, as most objects are still using all 40 bytes they've got available to them. And given this, if we were to keep slots aligned to cache lines, each 40-byte RVALUE would need a 64-byte slot, which, as we discussed earlier, wastes 24 bytes per value.
And that's it, folks. In this talk, we looked at how Ruby's memory allocator and garbage collector works, some of the issues in Ruby's memory layout, how we're trying to solve them with variable width allocation, as well as our current progress in the project.
We're continuing to improve the implementation, but we still have a long way to go. Thank you for listening, and thanks to RubyKaigi for having us.